Hi everyone, today we'll be looking at an IB physics question from the exam of May 23, and this is a question that has quite a lot of topics in it, and I struggled with it a lot as well back in the time, so let's go ahead. So it says that a toy rocket is made from a plastic bottle that contains water, air is pumped into the vertical bottle, and then the bottle travels vertically upwards, okay? The variation with time of the vertical velocity of the bottle is shown. Okay, so the bottle reaches its highest point at time t1. So we can actually derive that because the vertical velocity is 0 at time t1. And we can also say that from here, the velocity decreases as the bottle continues to travel upwards. And then when it's at its highest point, its vertical velocity is 0. And then it returns to the ground at time t2, which means that from T1, from its maximum height, it continued to travel downwards with an acceleration, and then at T2, it hit the ground with a vertical velocity of 10 meters per second. Okay, the bottle then bounces, the dashed line is the bounce. Okay, so it says estimate using the graph the maximum height of the bottle. So here it says using the graph, so you have to look at the graph to actually calculate the maximum height. So the maximum height is actually the displacement of the bottle from this position to its maximum height. So the displacement can be derived from the area between the vertical velocity and time graph. So this area, we can actually calculate the displacement, thus the maximum height. So if we look at here, we can say that 1.2 seconds maybe. And then here, this is about, let me delete it and see. Yeah, this is about 12 meters per second. And then this is a triangle. So if we just did 12 times 1.2 over 2, we would get 6 times 1.2 and then 7.2 meters. And in the mark scheme, it also says that it can vary between 6.4 and 7.4, if I'm not wrong. So 7.2 is the maximum height of the bottle. And then it says estimate the acceleration of the bottle when it is at its maximum height. So when it's at its maximum height, the vertical velocity is 0, and then it doesn't have anything else. So of course it will be the gravitational acceleration, which is 9.8 meters per second squared. It says then the bottle bounces when it returns to the ground. It is talking about this dashed line here because when it hits the ground, it then bounces, and as you can see, it has lower vertical velocity than before. It says calculate the fraction of the kinetic energy of the bottle that remains after the bounce. So to calculate the fraction of the kinetic energy that remains, what we would normally do was look at how much, look at the fraction of the final kinetic energy versus the initial kinetic energy. And we can calculate kinetic energy from 1.1 over 2 times m times v squared. But here we don't know the mass, and it's not important because mathematically you can just say that this is v final squared over v initial squared. So if you had to look at the graph before the bounce and after the bounce, the vertical velocity, we can say that before the bounce, before the dashed line, the vertical velocity is 10 meters per second squared. And then after that, we can say that about 4.5 meters per second squared is the final velocity after the bounce. So what we can say here is 4.5 over 4.5 squared over 10 squared, which gives us something about this, if I'm not wrong. And this equals to this and 1 over 5. So this is the fraction that we have to find. The mass of the bottle is 27 grams, so it means that 0.027 kilograms is the mass of the bottle, and it is in contact with the ground for 85 milliseconds, and this also means 85 times 10 to the power of negative 3 seconds. And then it says that it asks us to determine the average force exerted by the ground on the bottle. Okay. So in order to determine the average force exerted by the ground on the bottle, we of course have to use this formula from our data booklet because the average force exerted by the ground on the bottle is the change of momentum over change in time. So we already have change in time. We already know that the change in time is 85 times 10 to the negative power of 3. And then to calculate the change of momentum, we'll have to look at mass times the change of velocity. So our mass is 0.27, and then change in velocity can be calculated by V final minus V initial. So this basically means 4.5 minus 10, because our initial vertical velocity was minus 10 meters per second. And this basically tells us about the direction of the velocity. And this is 14.5. And then what we'll basically do is 0.027 times 14.5. And then this basically comes around to 4.6 newtons, if I'm not wrong. But this is not where our question finishes. And I was confused about this for a while too, because it asks us the average force exerted by the ground on the bottle. So we also have a normal force that is not taken into consideration if we leave the question here. And the normal force is mass times 10. So 0.027 times 10 is 0.27. And this equals to around 0.3 newtons. And then if we add up 0.3 newtons, our final answer will be 4.9 newtons, because there's also a normal force that the ground exerts on the bottle that's not taken into consideration with just 4.6. Okay, so after a second bounce, the bottle rotates about its center of mass. Let's talk about here. The bottle rotates at 0.35 revolutions per second. So when we say 0.35 revolutions, we're actually talking about frequency, right? This is the frequency of the motion. And to calculate period, we have to do 1 over f. So 1 over 0.35 will be our period, the time it takes to complete one revolution. So we have to take this into consideration when we're solving the question. The center of the mass of the bottle is halfway between the base and the top of the bottle. So this means that this area right here, which we can consider r, it's its radius, is 0.14 meters. Assume that the velocity of the center of mass is 0. Okay, calculate the linear speed of the top of the bottle. So what we can do here basically is we can just say V equals 2 pi r over t. So 2 pi times 0.14, and then 1 over 0.35, which is going to equal to 0.14, 0.35. And this is going to equal to something around 0.31 meters per second, if I'm not wrong. And this is our linear speed that is at the top of the bottle here. The next question asks, the maximum height reached by the bottle is greater with an air-water mixture than with only high-pressure air in the bottle. Assume that the speed at which the propellant leaves the bottle is the same in both cases, okay? So if the velocity is the same, we can just say the change of momentum is equal to mass times change in velocity, right? So momentum equals mass times velocity. So velocity is constant, it doesn't change, right? Explain why the bottle reaches a greater maximum height with an air-water mixture. So when we look at the question, we can just say that if it's only high pressure air in the bottle, the mass will be lower. But if we have a mixture consisting of both air and water, of course, the mass will be greater. If the mass is greater, then from a direct proportional relationship, momentum will be greater too. So the change of momentum being greater basically means a higher so basically, if the change of momentum is higher, it means that the propellant, the bottle, will leave where it's based at with a greater force. And if it leaves there with a greater force, that means that it's ultimately going to reach a greater maximum height. So if we had to explain it, of course, we would say the change of momentum is greater. Thus, the force with which it leaves the propellant is going to be greater, and then the maximum height is going to be greater as well. So that's where the question leaves us with. Thank you so much for listening to the first question that I solved. This is the first to many that will come in the future, but stay with physics. Love you all. Have a nice day.